Hi, everyone. Welcome to Quantum Machine Learning, Cutting Through the Buzzword BS. I'm hoping that all of you that are here today are here to come learn about quantum computing and machine learning. And judging by the number of you in this room, I'm kind of assuming that probably some of you have come here because you've heard some combination of buzzwords on the internet about this, and you want to come and discover what is kind of real and what is just BS. Going to give you advance warning for this talk. We are going to be covering a lot of different things, and we're going to be moving really fast. Please do not stress out if 70% of what I tell you today doesn't kind of stick and you feel completely lost. We're going to be focusing on a breadth of concepts rather than depth. It is not possible for me to give you all like a really good, concrete, deep understanding of quantum computing and quantum machine learning in 45 minutes. So think of this talk as more of a way to just get familiar with the field and then go away in your own time and really like dig into the concepts to kind of really like solidify your understanding. We're going to be talking about machine learning, we're going to be talking about quantum computing, we're going to be talking about hype in the industry. We're going to be bouncing around between a lot of different things. So buckle up and enjoy the ride. Just to get us started, a little bit about me. My name's Abby. Started off as a web developer, actually, in my career, and ended up moving into quantum computing back in 2021 when I became a developer advocate at IBM in their quantum computing department, and now I lead a team of developer advocates. I focus on quantum computing, open source, and developer education in general. There's my website if you want to go have a look at more of the things that I've done over the years. I'll just leave that up there for a second. Okay. What is quantum machine learning, or QML for short? This might seem like probably the ultimate combination of technology buzzwords, but is this a real profession? Is this a real thing, basically? Well, I found this definition online about what is quantum machine learning, and this definition says that it's an interdisciplinary field that combines quantum computing and machine learning techniques to solve complex computational problems more efficiently than classical computers. It leverages the principles of quantum mechanics to perform certain types of calculations exponentially faster than the best-known classical algorithms. Quantum machine learning is still an evolving field, and researchers are exploring its potential applications and limitations. And this lovely quote came from ChatGPT. It's not a talk in the machine learning track in 2023 if you don't have a ChatGPT reference in there somewhere, am I right? So now that we have a definition of what quantum machine learning is, let's fact check this for a minute. First up, that first sentence, quantum machine learning is an interdisciplinary field that combines quantum computing and machine learning techniques. Pretty vague statement, but I would say this is generally true. And I think it also speaks to the vagueness of the field in general. Quantum machine learning can mean a lot of different things, but at its core, it's some combination of quantum computing techniques and machine learning techniques. The next up we have here, solving complex computational problems more efficiently than classical computers, and exponentially faster than the best-known classical algorithms. This part of the definition is misleading, in my opinion, for a couple of reasons. Number one, it conflates the definition of what quantum computing is with the definition of quantum machine learning. Basically, it just found a definition of quantum computing and stuck that into a paragraph and said it was about quantum machine learning. These things that you see here are most normally talked about in the context of quantum computing in general. It's not unique to just machine learning. The second issue that I have with this sentence is that it is very confident, much too confident in my opinion. The tone of this sentence makes it sound like this stuff is a reality today, but spoiler alert, we are not there yet. We are, working towards this. We are hypothesizing that we can do this at some point, but we don't really have enough concrete evidence to demonstrate that this is true yet. And then the last sentence, it's an evolving field with researchers exploring its potential applications and limitations. Yeah, I would say that is a true a true statement. So overall, in this statement, I would say it's roughly 70% correct. And I like to test out definitions of quantum concepts with ChatGPT because the answers that these kind of AI models give you are, in my opinion, almost like a litmus test for how much the general kind of public on the internet understands the concepts. Because these definitions are just generated from the information that is available out there on the internet and how much people out on the internet posting these things understand the concepts themselves. So this, to me, indicates that there is definitely a certain amount of misinformation and hype around the topic of quantum computing and quantum machine learning in general. Which brings me on to this lovely diagram. If you were in one of the keynotes yesterday, you might recognize it. Machine learning is inherently a very difficult topic to understand. Maybe it's a little bit easier if you have a technical background. Quantum computing, I would say, is probably even more difficult topic to understand. So with quantum machine learning, you have this perfect storm of a really technically challenging field to comprehend. And when you have these very complex technical fields that people don't understand, this is when we get this kind of rise of misinformation, of buzzwords, of hype. And I would say I want to give the people the benefit of the doubt, and I reckon that a large amount of this hype and misinformation is genuinely unintentional. People don't really know much about the topic, but they're really excited by it, and then they can, it leads to kind of overpromising, making statements that aren't exactly true, which then perpetuate. Sometimes it's not all with the best intentions. Sometimes it's probably a bit more nefarious. People sometimes also try to ride this wave of hype, normally in order to sell you something. So it's just something to be aware of when you're being kind of someone who's on the internet and trying to figure these things out for yourself, just to always take what you're seeing with a bit of a grain of salt. And in my opinion, everyone is going through this Gartner hype cycle that we have here. This is generally used to talk about, a field in general, about how, when a technology first comes on the scene, it results in a huge amount of inflated ideas of its promises for the future, normally followed by a very steep decline into this trough of disillusionment. And then the hope is that unless the technology dies in that ditch, that then people will start to actually come into this slope of enlightenment to where you can actually do useful things with the technology. I think that every single person is going through their own version of this cycle. And my job as a developer advocate is to try and help you go from this kind of pathway to this kind of pathway. So for some of you in the room, maybe if you're right now, when it comes to quantum machine learning, at that peak level, you might actually find this talk a little bit disappointing. On the other hand, if you're in your trough of disillusionment right now, hopefully this talk helps you become more optimistic about the field in the future. So that is the journey that we are all aiming for here together in this room. Now, before we can understand a little bit about what quantum machine learning is, we need to take a step back and understand a little bit about quantum computing. I cannot teach you enough about what quantum computing is here in this talk, as well as everything else I want to talk about. So this is my quantum computing TLDR slide that I normally add to all my talks. First thing to understand is quantum computing is a type of computation based on the principles of quantum mechanics. Specifically, you might have heard about terms like superposition, entanglement, and interference. Go and Google them while we're on the talk right now. You'll find plenty of resources out there that can explain it to you. The research around the field of quantum mechanics in general has been going since the early 1900s, and then has slowly morphed into quantum computation research, which was pretty much entirely theoretical until 1998, when we managed to build the first real quantum device. And these devices, instead of using bits like a classical computer with 0 or 1, you can think of them as just electrical switches that are on and off, quantum computers use qubits or quantum bits. The difference between a binary bit and a qubit is that if a bit is essentially a really small switch that is on and off, a quantum bit is a subatomic particle. So we're talking like apples and oranges here, like very, very different paradigms of computation here. One day we hope to be able to leverage this technology to be able to solve the types of problems that are too complex for classical computers today to be able to solve, but the fidelity of the machines themselves is a blocker, and noise is a very big challenge that we have to overcome. We're going to talk a little bit about that more later. And today, like right now, you can actually write code and run experiments on real IBM quantum computers using quantum computing SDKs like Qiskit, which is the open source software package that I primarily work to support. It's an open source toolkit, and it's essentially a compiler. It allows you to write code in Python that can then get compiled down into something that a quantum machine can run and get results from. Next thing, we're going to take a little tangent, stop by to the field of complexity theory, mostly because I always get the same question, which is like, what can we do with quantum computers? Like, how do you kind of rationalize what these machines are actually built for, or why we're even doing this work in the first place? And to really understand this, we have to understand complexity theory, or what are computers for, quantum computers for. Starting at the kind of broadest level, we have this whole kind of graph is called P-space, and these are problems that are solvable in a polynomial amount of memory, so basically where space on your machine is not the limiting factor. And then within that, we have a bunch of different subspaces within that. MP problems are ones that are pretty easy to check computationally. And P problems are the easiest ones of that section. It's very efficient for classical computers to compute the answers to these. On the other end, the most difficult class of problems within MP space is MP complete. These are problems that are the most difficult for a classical computer, or a quantum computer actually, to solve. And then the most interesting section here is this BQP area. These are problems solvable in bounded error quantum polynomial time. That's what the BQP stands for. And these are the types of problems which we theorize will be efficient for quantum computers to be able to solve. And notice that the P at the bottom here is entirely kind of encapsulated within BQP, because it is theorized that anything that you can do on a classical computer, you should also be able to hypothetically do on a quantum machine. So what kind of problems actually fit into these categories? Well, at the easiest, like bottom P box level, multiplication is an example of the type of problem that is super easy for classical computers to be able to solve. On the other end of the spectrum, in the MP complete box, we have problems like the traveling salesman. And then we have a few things in the middle that we know are computationally expensive for classical computers to be able to solve. Things like integer factorization, discrete logarithm, and I put simulation of quantum systems in there as more like a general category rather than a mathematical problem. But these are the types of problems that very quickly we struggle to compute solutions to with classical computers, but which theoretically should not have the same blockers on a quantum machine. But I say all of this stuff kind of hypothetically and theoretically. That's because we don't know yet the limits of what classical computers can do. And there is some debate around whether does P equal MP. Can we theoretically do all of these things with classical machines? We don't know yet. And so that's why it's also quite difficult to say when is a quantum computer going to be better than a classical computer, because we don't yet know what the limit of our classical computation is. Okay, so now we kind of have an idea for the space of what types of things we want to be able to do on a quantum computer. How do you actually go about using one of these devices? Well, first up, you're going to start with your problem. And this could be anything that's kind of based in a mathematical problem that is really difficult to solve on a classical computer. Maybe this is estimating ground state energies of a molecule. Maybe it's doing some pretty much any mathematical thing that you can imagine is really hard on a classical computer. Once you have a problem in mind, then you need to come up with a quantum algorithm that you think will solve this problem. And what a quantum algorithm is under the hood is basically just a bunch of quantum circuits. A quantum circuit is, if you're familiar with classical computation, when you go down to the lowest levels, you can get these circuit diagrams where the lines represent bits and then the boxes on them represent operations that you do on them. We have a similar concept in quantum computing where we talk about the lines on the graph as qubits, and then the boxes on them are operations on those qubits. So you can kind of create a quantum circuit diagram that implements a certain algorithm to solve a specific problem you have. Then we have to take that quantum circuit and then compile it into something that is going to be specific for the device we're going to end up running it on. And those devices can then either be a simulator, if you're using a relatively small amount of qubits and you just want to check verify that you're along the right tracks with your algorithm. Then when you want to go to much bigger problems, you move it onto a real quantum device. And now, how do we kind of deal with all of this using open source? Well, this is where Qiskit comes in at this layer of the stack. It's kind of this core library of functionality. We have kind of a circuit library. We have different compilation techniques. We have a whole bunch of things. Google it, go check it out. It's a very powerful kind of core functionality for quantum computation. But then also around all of this, we have a really vibrant ecosystem of other open source projects that are addressing other layers of this stack, right up to kind of applications level where you're like defining the algorithms, all the way down to like how do we make the hardware work better, or how do we make better simulators to verify our results. Okay, so we understand a little bit about what the process is now of solving problems with quantum computers, but where does machine learning come into this? Well, there are many different types of quantum machine learning. I'm going to talk to you about some of them. Specifically, I'm going to split this into two different categories: quantum enhanced machine learning and machine learning enhanced quantum. The quantum enhanced machine learning section, this is when I'm talking about this, what I mean is using quantum computing to do machine learning better. And there are a few different kind of areas to explore here: quantum kernels, quantum neural networks. I'm specifically going to talk to you a little bit about quantum kernels. And then after that, machine learning enhanced quantum. This is on the other side of the coin, it's using machine learning techniques to do quantum computing better. Quantum computing, as we say, we're still trying to push it forward. We're still trying to improve the processes by which we do quantum computation itself. And I think there's a lot of potential here to add machine learning techniques into that workflow to help us reach our quantum goals faster. And I'm going to talk to you about one specific example of using machine learning for error mitigation. Okay, let's get started with quantum enhanced machine learning. If, as I'm sure many of you are in this room, you're already familiar a little bit with machine learning, and you're probably familiar with linear classification. You essentially have two groups of data, stars and hearts, and you draw a line between the two. That's your linearly classifying your data. Very common machine learning technique. But what happens when you have data like this, when you can't draw a single line between each of the hearts and the stars in this example? Normally now what we think about is, okay, how do we transform this data into a format where we can linearly separate them? So we take a one-dimensional thing of data in that example and map it to a two-dimensional feature space. So that's what we've done here. We've gone from one dimension to 2 dimensions. And now it is much easier for us to linearly classify this data. We can draw a single line between the two. But how do we go from data that kind of looks like this in one dimension and map it to this higher dimensional feature space? Well, again, still in classical machine learning world here, normally you will use something called the kernel trick, which is a way to use a linear classifier to solve a nonlinear problem. You can normally find the way that this works is you essentially take your data, X and Z here, and then you have to transform that data somehow with some kind of function, and you can choose that function yourself. You need to be able to identify this kernel function in order to make this process work. The problem that we face in machine learning with this is that if you have a very large feature space, it becomes computationally expensive to estimate what that kernel function is. And when you have a maths problem that is difficult to compute classically, that is where quantum computing normally can step in, and you come up with ideas for how to map the problem into a quantum space and come up with a quantum computation-based solution to it. So what we can do here is think about how do we create quantum kernels to be able to speed up some of these machine learning processes. What is a quantum kernel? You can tell when I was making these slides, I was really hungry, and all this talk about kernels made me think about popcorn. So excuse my graphics. But yes, what is a quantum kernel? A quantum kernel is basically the same as a classical kernel. It works in the same way, but we use quantum circuits as feature maps, and I'm going to show you a little bit about those in a minute. Are quantum kernels inherently better than classical kernels? Not necessarily. You need to find a kernel function that you know is classically difficult to estimate before you can theorize that there might be a quantum advantage at play here. If you're just using a quantum computer to estimate a kernel function, which is really easy to do classically, there's no point of doing it on a quantum computer. How do you choose a quantum kernel? This process really strongly depends on the problem, the learning problem at hand. There are many different strategies for choosing a good quantum kernel, like using underlying structures in the data, or you can even train a parameterized quantum kernel using like a different type of quantum machine learning. But don't worry about that. We're not going to go into much detail on that today. OK, we finally have some code. This is kind of a very quick example I found of how you might come up with a regular machine learning kernel. You have some data, X and Y. You then map that data embed that data in a feature map. Here it's just some kind of NumPy array matrix. And then you create a kernel function based on that feature map. In this case, they're just doing the dot product. And then you can pass that kernel with a keyword argument to whatever support vector machine you're using of your choice. In this case, I just got one from scikit-learn. And then you fit the data. And that's normally the process that you use. This is kind of an equivalent process with quantum, with Qiskit and the Qiskit ecosystem packages. Here at the top, we have I put up the installs and some of the imports for you, just so you can get a bit familiar with some of the packages that are out there in this space, all open source. The first kind of 3 lines of actual code after the imports is just about establishing a connection to IBM quantum hardware. This is not the type of computation you can just do on your Mac, even if you have a very nice, powerful M1. Like I do, you will need to connect to a real quantum device somewhere through the cloud. In this case, I'm using IBM Quantum's backends. I'm accessing them through the runtimes, the Qiskit runtime service. Then what you need to do is you need to generate a quantum feature map. Here, there is a handy feature map class available to you from Qiskit. I just chose one. There are many different ones as well. I'll show you in a second what those look like. And then the last section is defining the quantum kernel, similar to what we did on the previous page. At this point, we haven't passed any of the real data yet to it. We've just done some setup here, and we've created the feature map and set up the quantum kernel class. Big caveat, this code right here does not provide you any advantage over the classical version I just showed you earlier. It is not that easy. Here, I was optimizing for what was the minimum amount of code I could write to stick it on a single slide in front of you, which, spoiler alert, should not be the techniques you use to optimize your quantum computation. Surprise, surprise, that won't get you very far. The accuracy and the quality of the results that you will get from this kind of work relies on many different things, not limited to, but including the complexity of the data that you're passing to your feature map, how you configure that feature map itself, and also the quality of the device and how you are customizing your circuits to what you know about the device topology and various different factors there. So just taking a moment to look into what the feature maps kind of look like. These are a couple of examples that I have for you here. This is what I was talking about earlier with these quantum circuits. Each line represents a qubit. Each box represents an operation that you're doing on the qubit itself. And the reason I wanted to show you this is because you can parameterize gates in a quantum circuit, and those parameters that you add kind of corresponds to how you rotations that you do on the qubits themselves. And those rotation angles is where the data that you are passing into kind of get implemented on the device. So here on the, I don't know if you can see the mouse. Yeah, you can. So here where you have kind of this x1, 2 here, those are that is your classical data that you are passing into it, and this is how it kind of gets represented in the quantum circuit format. These are two out-of-the-box feature maps that Qiskit provides, but you can also build your own. Remember what I was saying earlier, that sometimes you want to build a kernel that is very specific to the data that you're using. You would probably need to create your own custom quantum circuit feature map to be able to do that. OK, once you kind of have your kernel set up, you then can essentially just pass it to a support vector machine of your choice. So here I've, again, used the scikit-learn one. You take whatever data you want, and you pass your kernel in that kernel parameter to the SVC, and then you fit it. And this is, I like to show this because it really highlights how I think sometimes people assume that it's always a competition between quantum computation and classical computation. But I think in reality, the most useful progress we're going to make in this field is when you have this hybrid quantum and classical approach to solving problems here. So for example, here we did the kind of the kernel setup using the quantum device, and then we pass it to the existing kind of classical tools out there. And making those tools work together is normally a priority of open source developers in the quantum computing space. As I mentioned, a lot of open source packages out there to help you do this. I really recommend going and looking at the Qiskit GitHub organization, as well as the Qiskit community organization. The Qiskit one just has like the core SDK. The Qiskit community one has a bunch of other packages that are being developed from the community itself, not necessarily specifically from the Qiskit teams. Two that I recommend you go looking up is Qiskit Machine Learning and Quantum Kernel Training. And yeah, maybe see if there's anything that you can contribute there. OK, next up, excuse me, we have machine learning enhanced quantum. So this is using, now we've talked already about using quantum to make machine learning better. Now let's talk about how can we use machine learning to make quantum computing better. And I'm going to talk to you specifically about one example of research that just came out very recently on using machine learning for error mitigation, which means now we need to talk about noise and errors. And I kind of lied to you a little bit with this diagram because this is, I guess, maybe the ideal process for solving problems on a quantum computer. But in reality, there's like a big asterisk over this hardware piece here, and that the hardware that we have right now is still, it is getting better every year, bigger devices, more reliable devices. But you normally still have to do some kind of error mitigation or error suppression in order to get good results from the devices. And the reason for this is because of the physical limitations of the hardware itself. You may or may not have heard about decoherence or noise. Essentially, qubits are subatomic particles that are really, really difficult to keep in a stable state. They are very highly sensitive to external vibrations, changes in temperature, any different kind of environmental factors. Basically, they're really fussy bits of hardware that take a lot of effort to keep in that stable state. And essentially, the more qubits you have, the more connections you have, the more noise you get, which means that the results that you get aren't what you necessarily expect. You think it's going to return a 1 value to you, but half the time maybe it returns a 0. So how do we, when we do like 100 or 1,000 experiments on the device, how do we know how many of those results we're getting back are the real result? That is where we kind of develop these techniques for dealing with noise. Three main categories that you should kind of be aware of: error correction, error suppression, and error mitigation. They all mean very different things. Error correction is basically much more of a long-term goal. If someone is talking to you about error correction, just know that that's the one that's the furthest in the future in terms of development. And essentially, the way I understand it is it basically works by you apply specific gates onto a large collection of physical qubits in order to get a much smaller amount of logical qubits that are error-free. And you perform error-correcting code to detect the errors. Next up is error suppression. This is techniques that are much closer to the hardware that normally you as a user might not really engage with very much. It's normally kind of abstracted away from you by the hardware providers. So the techniques that are in this section revolve around concepts like dynamical decoupling or drag pulses. The last one is the one that is the most relevant for this talk, and that's error mitigation. These are things that you as a user can normally kind of configure, and there's a lot of research going into this at the higher level of the stack. And what this category of techniques does is it takes the outputs of lots of different circuit runs in order to kind of cancel out the errors of the kind of original ones. These ones can be quite intensive on quantum resources because you're not just running the circuits you need to solve your problem. You have to run a lot of extra circuits on top of that to kind of get a feel for what noise is there and then use those like results to then correct your original circuit run. So you end up having to kind of 2 or 3 times, 10 times even the amount of circuits that you're running on a quantum computer in order to enact these techniques efficiently. There's a few different techniques within this error mitigation category that are pretty popular. A very well-known one is zero noise extrapolation. It's also probabilistic error cancellation, and another category of techniques called M3 or T-Rex. For zero noise extrapolation, what this means is you're essentially taking measurements from many circuits at different levels of noise where you know how much noise there is, and then using those results to kind of extrapolate out what the error-free result would be. I know I'm giving you like very kind of vague answers to this. There's not a really good way to summarize all these different concepts in like a single bullet point, but hopefully this should give you a little bit of an intuition for what I'm talking about, and then you can go and like do a deep dive later. There is an open source project for this called Prototype ZNE. Go check it out. Next up, we have probabilistic error cancellation. This is basically where you sample a collection of circuits and then on average, they kind of mimic a noise inverting channel. An analogy that's often used here is think of it a little bit like noise canceling headphones, but not really. And again, there's an open source project called Qiskit QEC that does this. And then lastly, we have M3 and T-Rex, which are techniques that are focused specifically on reducing the amount of noise from measurement. When you're running a circuit on a quantum computer, you need to measure the result. And sometimes the act of doing that measurement actually is faulty. So the qubit itself says, hey, my value is a 0, but then the measurement says that it was a 1. So then there's something dodgy going on in the measurement process there. And there's an open source project called M3 that focuses on this. So now we understand a little bit about noise, about why it's a problem, different techniques that are out there, all kind of quantum-based techniques. I want to talk about this paper, Machine Learning for Practical Quantum Error Mitigation. This was a paper that came out only like a month ago now, less than a month ago, which was built by a very interdisciplinary team of quantum theorists, machine learning experts, coders, theory people, and one of the authors is actually here today at the conference. I don't know why he's not giving this talk instead of me, but anyway. So go and find him out there. He's got his IBM Quantum badge on if you want to ask him more questions about this paper in particular. Because this is so new, that this code, I believe, is open source, but it's not in a nice, tied in a bow, nice open source package that you can just install out of the box. You have to go and look for a little bit more. But I really recommend going and reading this and digging into the details a bit more. The TLDR of what this paper does is essentially they tested 4 different classical machine learning models: random forests, multi-layer perceptrons, graph neural networks, and linear regression. And they tested out these machine learning models and to see if they could error mitigate the results of a quantum experiment without having to essentially run extra quantum circuits to do it. They tested various different types of noise, like I mentioned. They used different quantum circuits, different sizes of experiments. For the very small starter experiments that they used, they found you could validate the results of whatever mathematical problem it was with the real world results, that you could just classically simulate the results. And when they were doing that, they found out that some of their best performing models actually performed better than zero noise extrapolation on those small devices. Specifically, random forest was the best performing model, which I think actually surprised the paper authors because it was one of the comparatively simpler machine learning models that they tested out. Then when they moved on to much larger experiments, at this point, you cannot really easily simulate the results. You're only relying on the quantum computer for the results. So all they could do there was they compared the results with what ZNE gave them, and they could tell that the classical machine learning method performed as well as zero noise extrapolation. And for all the experiments they run, the machine learning models required much less QPU resources. Because of what I said, they didn't have to run these extra circuits on real quantum devices. They were able to use classical methods to do that extra error correcting stuff so that only the QPU resources for actually solving the problem at hand was required. Okay, this is kind of like getting to the end of my little showcase for you all about quantum machine learning. The key takeaways that I would recommend that you take from this talk is, well, first of all, that part of that initial definition from ChatGPT, that quantum machine learning is very much still an evolving field. There are researchers exploring many different areas, applications, and limitations. And there are also many different ways to interpret this field, depending on what different research is going, what your interests are. Many different people involved in discovering what is out there within this subgenre of quantum computing. Not every quantum machine learning idea will lead us to quantum advantage. It's not a silver bullet at all, but some of them might. There are some really promising areas, like the ones that I showed you just now. And what is really clear is we need super interdisciplinary teams to be able to move the field forward. It's not, we don't just need quantum computational scientists. It's not just physicists we need. We also need machine learning expertise in this area as well. And on top of that, open source and open science are absolutely crucial. It's a very specific set of skills required for this field. There are not that many people out there that have the skills to do this stuff. So making all the information as available as we can and all the code as available as we can, really helps to generate more activity in this space and help us get to where we need to go faster. And the last thing I would say here is just embrace the uncertainty. I don't think I've given you a clear answer here on necessarily what even is quantum machine learning or where's it going to go or how impactful it's going to be. But that is just the waters that we swim in this field of quantum computing and quantum machine learning. And I actually really enjoy being in that space because we don't know what's going to happen, and it's super exciting. So I encourage you all to embrace that uncertainty. Okay, thanks very much, everyone. I think I have a few minutes for questions. Thanks. Oh, also, just while I'm answering questions, if anyone is interested in getting more involved in contributing to some of the open source projects that I showed you earlier, there's like a few different ways that you can do that. I'll just leave that up there. And I think I saw a couple of hands going up for questions. Yes, at the back there. Please shout really loud because I can't hear very well. How many qubits do we have so far? Well, so at IBM Quantum, oh God, we essentially double the amount of qubits every year. I believe we're on like 237 now, I think. Yes, yeah. In the hundreds, and we actually we have many of those devices we also make available free to the public. You get 10 minutes a month, I think, of QPU time, so time that you spend running something on a quantum computer. And just, I think, last week or 2 weeks ago now, we basically announced that we're only making 100 plus qubit devices available through this program. We're basically not continuing to support devices less than 100 qubits. So yeah, you have a lot of qubits you can go play around with now, which is amazing considering in 2016, when IBM first put their devices on the cloud, we had like 5 qubit devices. And now we're not even bothering to deal with those anymore. We're just doing 100 qubits or more. Over there in the back.
Sorry if you already covered this, but I've been reading about the different types of quantum devices.
Yes.
And it's a little unclear, like there's no one list out there that says, here's all the different ways you could do it.
Yeah.
Can you give a rundown on the options?
Yes and no. I mean, there's a reason there's not like a definitive list out there, because everyone's always like experimenting with new different types. There's a couple that are the popular ones. IBM focuses solely on superconducting qubits. There's also other organizations out there doing trapped ion qubits as well as another big category. And then I would say those are probably the 2 biggest ones to pay attention to. And then there's a lot of other like smaller institutions experimenting with different types that, yeah, I'm not qualified enough to speak on the details there. Yeah. The closer we get to the hardware, by the way, the less skills I have. As you can tell from this talk, I am a software developer in background. So the closer we get to hardware, the less information I have for you. Yes, here in the front. I don't think, so do you mean like storing data on the?
Well, if you're going to do large machine learning, and you need like gigabits of data to train on,
Yeah.
Are there issues currently with quantum computing and loading large sets of data into it?
Yeah, so I think that's going to be an ongoing challenge for us, and that's what we're really pushing the limits now. Like the number of qubits we have is not the only limiting factor. It's like how quickly can we process data on those qubits, and when we scale up to like thousands of qubits as well, like how quickly can we pull data through them. Quantum devices themselves, I don't think will ever store data. That's where I'm talking about kind of hybrid quantum and classical techniques are going to be super important, because you'll have your classical data center somewhere where or your hard drives where you're storing the data, and then you just like sequentially pass them to the quantum device. And then there's also work going into, if you're interested, go and look up the IBM quantum roadmap for devices. There's plans coming up to kind of like parallelize the hardware as well, so you can kind of split your computation across multiple devices. There's a lot of just like classical cloud engineering that also needs to go into propping up this industry. I think people tend to assume that you need a PhD in quantum physics to be able to do anything useful in this field, but there's a lot of classical software architecture and cloud-based infrastructure that needs to be set up to be able to handle exactly like the stuff that you're saying. So TBD, I guess, is the short answer.
It was a great talk, by the way.
Thanks.
I'm interested in, you were talking about the error correction. My mind is somewhat polluted by the classical processor. And you run something 1,000 times, you get the same answer, and if you don't, something's wrong. But I get the impression that if you're running it on a quantum processor, it's like an answer comes out with error bars, or you'll have to run it 1,000 times and get the average. Is that what you're saying?
Yeah, essentially that's what we do, and there is certain. Okay, I'm gonna try to give a short answer without going into too much depth. But depending on the type of computation that you're doing, a lot of it is you're running your circuit multiple times. And so you might end up, and this is because of like, have a look up like variational algorithms. Like the inherent advantage you're getting from the computation is that like you run it and then you adjust your parameters, then you run it and then you adjust your parameters. But then, you know, if you have to run something 1,000 results just to kind of get down to the correct answer, if you have errors in there, it will kind of like throw things out of whack. So a lot of the nature of the computation of the algorithms you're running necessitate running a lot of versions of the same circuit. And sometimes you'll get, you'll be able to see easily, oh, okay, 99% of the results kind of follow the trend that we're expecting, but then there's like a few outliers, and those are easy to cancel out. It gets harder when, 50% of your results are outliers, and then you need to kind of run even more circuits to be able to figure out what those errors are, and that's why we have all these error mitigation techniques to be able to see, like, okay, like what is an expected result versus one that we're not expecting. And how do we do that with minimizing the amount of time we're using on the QPU? Because these devices are very big and very expensive, and there's not very many of them, and everyone wants to use them. And the minimum amount of time right now that we can spend on them, the better. Yes. Sorry, could you speak louder? Yeah, so this is kind of related. So you're not loading data directly into the device itself. You have a circuit with kind of in those, I can go back to the diagram. Where is it? Here, so you have like these little slots kind of here in each gate where your data is getting loaded, but you'll have like this one circuit, and then depending on how much data you have, you might need to run this circuit like 10 times or 1,000 times, depending on how much data you're loading in. And you can also parallelize it differently. So here on this one at the bottom, you only have like 2 qubits involved, whereas in the top one, you have 3 qubits involved. So there's many different ways to tweak like how much data is being processed at once by this quantum feature map, essentially, yeah. But essentially, like you can create these circuits by saying, I want a parameter theta in this slot, and that's where the data kind of gets chucked in when you actually run it through the when you evaluate it at the end. Okay, any more questions? I think we're kind of at time actually. Maybe I need to get off the stage. But yeah, if you have more questions, I'll be hanging about here if you'd like to catch me afterwards. Thank you very much, everyone.